In this video, I'm going to explain how to solve systems of equations using a method called substitution. For today, there are two important questions. First, if we try to graph a system of equations, linear equations, and the answer on the graph isn't exactly clear, then what can we do? And second, how can we use the substitution method to solve a system of linear equations? First, let's briefly review how to solve a system of equations with graphing. So we have these two lines we've graphed, and we can see that they intersect at some point, but you notice that that point is not at the vertex of two integer values. It's somewhere between 3 and 4 on the x-axis, somewhere between 0 and 1 on the y-axis. So if we're looking for the solution, the point that satisfies both these equations, the graph does not clearly show that to us. So graphing is not the best way to solve this problem. But what else can we do? If graphing isn't working for us, if it's not clear exactly where the lines are intersecting, instead we can just use algebra. We can do away with the graph entirely and just focus on the algebraic equations that we have for this system and manipulate those equations using the algebra rules that we know, and we can find x and y. Because remember, our solution is still going to be a point, x comma y. Our solution will still look like that same form. We don't need the graphs, we can just use algebra. So one algebra method that we can use is called substitution. And it's important to look for a variable, either x or y, that's already alone. So if we look at this system, we can see negative 7x, negative 2y, another negative 2y. Those are not good candidates for substitution because they have coefficients. But we have this one x that's already by itself, just x, positive 1x. So that's a good candidate. So we want to isolate this x on one side of the equation. It's already alone without a coefficient, but we want it alone on one side of the equation. So we can move this term negative 2y by adding 2y to both sides, and we get x equals 11 plus 2y. So now we've got x alone and isolated on one side of the equation, and we have an expression that's equivalent to x on the other side. So now we have x equals 11 plus 2y. So x and 11 plus 2y are equal. They are the same thing, essentially. The same way that 10 and 2 times 5 are equal. X and 11 plus 2y are equal. So that means anywhere we see an x, we can replace it with 11 plus 2y because they're equal. For example, in this top equation, you can see negative 7x minus 2y equals negative 13. So that x in negative 7x can be replaced, and it'll become negative 7 times the quantity 11 plus 2y. Minus 2y equals negative 13. After making that substitution, this equation now only has the variable y. There's no x anymore. So we can use the familiar algebra rules that we always use, like distribution and doing the same operation to both sides of the equation to solve for y. So now that we've done all these calculations, we found y equals negative 4. Great. But we're not done yet. Remember, we're looking for a point, x comma y, where these lines intersect. So we need both coordinates. We've got y, great, but we still need x. So now we can take this y value, this negative 4 that we found, and we can do another substitution. In that equation where we isolated x equals 11 plus 2y, we can now replace y with negative 4. So now once again, we have an equation with only one variable, only x. So we can do our usual calculations and we can find that x equals 3. So now we have both x and y, 3 and negative 4, and we can put those together as the coordinates of our solution, 3, negative 4. So that means if we actually went ahead and graphed both of these equations in our system, we would find that point of intersection, 3, negative 4. You might remember from a previous video, some systems of linear equations have no solution. If the lines are parallel, they never intersect, and there's no point that satisfies both equations. So what would finding a result like that look like if we're using an algebraic method? So in this example, you might notice we have negative 3x, 3y, and negative x that are not alone, so they're not good candidates for substitution, but this variable y is already alone. So our next step is to get that y by itself on one side of the equation. So we can add x to both sides to make that happen. Now we've got y equals this expression x plus 3, so we can replace y in the first equation with x plus 3. So now that we've made that substitution, this equation is ready to be solved for x. So we do our process here to try to solve for x, and we find 0 equals negative 5, which is kind of strange because that's not true. Ideally, we would find y equals something or x equals something, but instead we have 0 equals negative 5, which is a false statement. If you're solving a system of equations using algebra and you come across a false statement like this, that means your system has no solution. And graphically, that means that the lines are parallel with no point of intersection. So to wrap up, let's go back to those two important questions from the beginning. First, if the graph of a system of linear equations does not show us clearly where the solution is, what can we do? We can use algebra to solve the system instead. We can manipulate the equations with no need for the graph at all. And second, how do we use the substitution method to solve a system? So first, identify which variable is already alone without a coefficient. Once you've done that, isolate that variable on one side of the equation. Whatever you find as the expression which equals that isolated variable, replace that in the other equation in your system, which will allow you to solve for one variable, which you can then plug back in to your isolated equation and solve for the second variable. If you follow this process and you end up with a false statement, that means your system has no solution. That's all for today. I hope you enjoyed. I hope you learned something. Thank you for watching and have a great day.